Good. Recording started. Now let me share the screen. And let's share this one. Just a second. Okay. Okay, can you please confirm that you see my screen or not?
Yes, it's okay.
Okay, and you see the screen with my website, correct? With,
Yes.
Yes.
Good, perfect. Okay, we can start. We are successful. So, good morning. This is our second lecture. It is actually the first lecture online. You know that this course, the subject is taught in a hybrid mode. On Monday, I am in physical presence, and on Thursday, I am online. Okay, this will be the same articulation up to May. It's an experiment because, you know, during the pandemics, we were teaching online, but after the pandemics, the university requires that we teach in physical presence. But a few courses are allowed to adopt an hybrid mode. I decided to apply for it because I think that the particular articulation of our course and the subject also, I think lend themselves to a successful and productive integration of different teaching modes. So I think that with the virtual participation, we may also use some features of the technology that we cannot use in the room. And so let's see. I'm also curious to know your opinion. And I will gauge your opinion during the next lectures. Today, I am expected to teach for 2 hours. If you don't mind, I will make a break after 45 minutes, around 10, a break of 10 minutes, 5-10 minutes, just because I want to check, given that it's the first lecture, I want to make sure that I'm not abusing of your attention too much. Yesterday, I taught in Ravenna for 4 hours virtually, and it was a bit tiring. Okay, 4 hours is twice 2 hours, so it's a different case. But I realize that, you know, when you are in presence, there are more breaks. It's more relaxing. So let's try to make a break, if you don't mind. If you have any problem, because of course making the break, we will close the lectures at 11, 5 to 11. So if you don't have any problem with this timing, let's try this way today. If you have any problem, just write in the chat or step in with the micro. In general, don't be shy. If you want to step in with the micro, this is perfect. I mean, given that this is a virtual lecture, I appreciate very much if you step in, because as you know, in the virtual mode, to interact may be a little bit more difficult with respect to the physical presence. So I really appreciate if you step in, and keep in mind that there are no stupid questions. I think it's more likely that there are stupid silences. So don't worry. Really, I appreciate if you step in. Okay. Now, last time I just introduced you to my website, to the page where you can find the tutorial. It's this one, the link that I am pointing with the mouse now. And here we saw that there are several links for our next lectures. As I mentioned to you, I am repeating it because I want it to be clear. This list of lectures, which you can see here, I am making a selection now, it's provisional. This means that probably more links will come and some of the links will disappear. Okay, so this is just a first tentative outline. Last time we clicked on the introduction, and as you may remember, my opening it, we looked at this presentation here, which is interactive, and we browsed it. And I stopped at the last slide, which I am going to now. And I said, okay, read this slide by yourself. Okay, I had a second thought to it, and now I prefer that we comment a little bit more on it, because I want to comment on the definition of science that you see here, because I think it is extremely important, given that climate change adaptation is based on a scientific approach. It's important that we agree, we fully understand what is science, which we can define, as you can see here, as a systematic effort that builds and organizes knowledge in the form, and this is the important part that I want to emphasize, in the form of testable explanation and predictions about the universe. So the term testable here is essential. Science is objective, and its conclusions should be supported by testing and validation. This is not always possible. Okay, so it's not always possible to validate our results. So sometimes, in principle, we try to validate them, but the validation cannot be considered complete. This is particularly valid for climate science, because we don't have a large set of data that we can use. Just 1 second, I want to look at the participants, because I think there are some participants in the waiting room. Okay, now admitted it. So, as I said, we don't have a large set of data to make testing, and therefore sometimes in climate science and also in water science, in all the sciences connected to climate and environment, in some cases, our testing is, let's say, partial, it's incomplete. Okay, that's fine. Just to be aware that the fact that validation is incomplete means that there are unknowns still, a lot of unknowns in science, and especially related to the climate, related to the environment, there are several things that we still don't understand. This is particularly important because today we live in a period where we are given the feeling that we can predict everything. Actually, if we look at our day-to-day life, we realize that this is not true. We realize that we cannot predict everything. We realize that sometimes we try to make predictions, but they are wrong. And we have to understand that the same situation is replicated here. When we talk about climate, when we talk about environment, when we talk about sustainability, there are several things that we still don't know. For instance, I give you an example. We still don't know what happens to rainfall once it reaches the ground. We know that after a while we see water in the rivers, we see water in the underground, we see water in the sea at the end of the story. But we actually don't know what's happening in between. Does water travel along the surface of the earth or in the underground? Okay, we know that it travels both on the surface and in the underground. But what is the percentage? What is the percentage of travel over the surface with respect to the travel in the underground? We don't know it. And we can get an idea of what happens, but actually we don't know the details. We don't know what happens to a drop of water when it reaches the ground in between while this drop is traveling towards the ocean. This is important to know. In fact, the history of science is studied with erroneous conclusions, because validation, testing, the interpretation of the results was wrong. And we have to be fully aware of that. These errors, these erroneous conclusions could be repeated if we don't pay attention, if we are not critical enough. I just wanted to emphasize a little bit more these aspects related to science, which are extremely important. We have to be fully aware of what is the uncertainty in it, but we will talk about uncertainty again. Okay, good. Now let me close this presentation, and let's pass to the second link of our list. So let me go back here. Good. And the second link is a premise. I want to make it very short, okay? But I want also to make clear to you what is the learning process that we adopt here. And let me start by saying that the panorama in education has changed a lot in the last 10 years. I think I already discussed on Monday with you on this. It changed a lot, not only for the pandemics, but also because there were changes, and changes in that are mainly due in the changes that we experienced in the information channels. With respect to 20 years ago, the way we get information is radically different. 20 years ago, we were used to get information from books. We were used to study by using books that were perhaps 20 years old. Now we live in a period where information becomes very quickly obsolete. So when we use information that is dated 2010, for instance, we are now used to consider that it's too old in science, which was not the case before. When I took my degree, I got a degree in 1992. I was studying over books that were published in 1970, so 20 years earlier, and that was perfectly fine. Now the information is changing more rapidly, and the internet is giving a lot of opportunities to get information. So the skills that you need as a student and the skills that you will need in engineering to carry out your job are also changed. You need skills that were not needed 20 years ago. There are skills that were needed 20 years ago, which are not needed anymore today. So I want to draw your attention very quickly on a Wikipedia page, which is focused on the so-called 21st century skills. And this page, let me open it. This page basically discusses what I was talking about. So what are the skills that are today needed in the 21st century? And let me go back to my web page and look at this picture here, which is copied by the Wikipedia page, by the way. This is a public domain picture. And please have a look at it. I'm not commenting. Just have a look at the skills that are considered, according to the source, Wikipedia, to be the key capabilities that we need to gain in the 21st century. I think it is extremely important because it helps you to build your CV, to build your skills, and to improve your chances to get in the job market with full reward, with full satisfaction of your expectations. And just look at these skills. I think it is very clear what they mean. So I don't think we need to comment. It is less clear how we can improve them. And if you want, we can discuss further later how we can improve our flexibility, how we can improve our literacy, how we can improve our creativity. This is less clear, but we will have several opportunities to discuss this. And the last thing that I want to say about this introduction, look, this web page is not a matter for the exam. It's just something, is food for thought, which I am providing because I want to stimulate you, if it's possible, to take this subject, this course with not a different, but with a perspective that is looking forward. It's not different from the other perspectives that you adopt with other courses, but just try to look forward beyond your degree, beyond the exam. And when I was a student, I was studying for the exam and then for the degree, and I didn't look much forward. It's not needed, but it helps a lot. It helps a lot in order, as I said, to get full reward once you play your cards in the job market. Finally, what I would like to do here, and I will start already next week, is a bit to reverse the the approach to education. The classic approach started from the theory. So you have to turn the arrows here about 180 degrees in order to get to the traditional approach. We used to start from the theory. So when I studied engineering, I had a full 2 years of mathematics, geometry, and also a lot of studies on physics for 2 years. It was just theory. And then from the knowledge of the theory, you build models. Models means methodologies to make design. These models give you what are called here design variables or design event. So the essential element to make your project. And models are fed by data, of course, by information, which we don't have much in climate science and in hydrology. And then in the past, from this design variable, from this design project, we got the solutions. Now, I think I would like to revert the cycle. I want to start from the solutions, from what we need. So we need climate change adaptation, how we can adapt to a changing climate. Should we build a dam, for instance? Should we refer to nuclear energy? Another example, this is the solution. And then once we identify the solution, we need to understand what is the information we need to make the design variables. And then once we know the design variables, design events, we understand what kind of model we need to produce these design variables. And then we understand what kind of data. And then once we realize that we need a certain model, like a climate model, then we can study the theory. I think this approach is more efficient because you limit the study of the theory to what you really need. For sure, it's more efficient. There is a risk in this approach that you are missing pieces of the theory that are not strictly needed, but are still useful to build your perspective, to build your information. Let me make an example. Today, we don't need analytical integration anymore. We don't compute integrals analytically. The integral is a sum. So today, we make this sum with the computer. We use numerical integration. It is much easier. It was not possible in the past because we didn't have computational resources. We didn't have a personal computer. Now we can use numerical integration. It is much easier. It is more easily understandable because the integral is a sum. So it is very easy with a computer to make several pluses, several sums. On the other hand, we cannot say that analytical integration, the knowledge of analytical integration is useless because through analytical integration, we understand what an integral, how an integral works. We understand the concept. Numerical integration doesn't allow us to understand the concept. Let me make another example. Today, we don't need to write codes anymore in the computer because there are codes prepared for everything. If we go on the web or we go in the market, we can find a code for everything. So the result is that even in engineering, we don't focus much on coding, preparing your own code. Because in several situations, it is useless. I discussed about this on Monday. On the other hand, if you use a code that is prepared by another person, by another entity, by another company, you don't know how it works. If there is a mistake, at the end of the story, if the code is bugged, you cannot say it's not my responsibility. It's your responsibility as an engineer if you produce an erroneous result. So there is an increased risk of making errors because you don't know what you are using. If you know how a code is written, you can understand if it is correct or not. So this is another example to tell you that this approach that I am following limits the study of the theory to what is strictly necessary. but be careful, because the study of the theory in general, it's not useless. You have to be able to recognize what is not strictly needed, but still useful to improve the skills we talked just a few minutes ago. Okay, of course I will guide you, but try to understand how I make the selection of information. Try to understand if I make exceptions, like there will be some cases in which I will say, look, this theory is not really needed, but I think it is useful. Try to understand my train of thought and make questions if something is not clear to you. Okay, I will give you an example probably already on Monday. I need to introduce you to probability, because this is essential to study climate change. And I will focus on the solution, on what we need. And therefore, the theory of probability, we will not speak of it very much. It will be a very, very brief treatment, what we will do together. This is an example, because I don't think we need to study the whole probability theory to talk about climate change. And therefore, I will limit our discussion to what is really needed. Try to understand what's the difference between the traditional approach, because I'm sure that most of you studied already probability in their career. Okay, let's close with this, and just have a look if you are interested. And I suggest that you have a look at this page, but again, this is not a matter for the exam. You will not find any question related to this web page. Good. Do you have any questions so far? Perfect. Let me look at the chat. I don't think there is anything. If you write something on the chat and I don't, you realize that I'm not reading it, just step in with the micro. Okay. Now, I would like to start a new lecture, which I think it is exciting. I'm looking forward to it. It is new. I prepared it about 1 month ago. And so if you see something that is not clear or something that may be wrong, like typos, please send me an email or step in with the micro and I take notes. So the lecture is called the Earth System, because you know, we need to talk about climate. We need to understand climate change. And therefore it is needed that we gain some understanding on how the Earth system works. So this lecture is given in the form of a web page, of course, but you have a PowerPoint at the end to download, which I am using for delivering this lecture. I go to the end of the page and you see there is download the PowerPoint presentation. I just uploaded it, so it was not there yesterday. Let me download it. You see that if I go to downloaded files, there is a PowerPoint. Let me open it. It was open with LibreOffice. Let me open it with PowerPoint. Just 1 second, and I extract it in my desktop. Probably you don't recognize what you see on my PC, because I'm not using Windows. I am using another operating system. I am using Linux, for your information, but we will talk about it later. Okay, here is the PowerPoint. Now let me put it in the presentation mode. So what is the Earth system? The Earth system is the aggregation of all the processes that are occurring in nature. Okay. And when we talk about the Earth system, some people include in the domain of Earth system also planetary sciences, because of course Earth takes the energy to engine all these processes from the sun, and the sun, strictly speaking, is not part of the Earth system, but it is providing the energy. So in a wider perspective, some people include in Earth sciences also solar and planetary sciences. Let's focus for now on the Earth processes. Of course, we will need to discuss about the inputs and of energy, and then we will talk about the sun. But let's focus our discussion, detailed discussion on the Earth processes. Okay. Now, first of all, there are two ways which you can look at the Earth system. Let me just open again my website, because I need also to have a look at it. I put it on the other screen because otherwise I run the risk of forgetting something. Okay, as I said, there are two ways of looking at the Earth system. There is a traditional called reductionist view, which splits the Earth system in components and studies these individual components one by one. For instance, water cycle. Another example, carbon cycle. The water cycle is a subset of Earth system processes. Good. So why do we need to split the processes in groups, in subsets? Because it's easier to study them without, if we look at the whole set of processes, so we have to study the water cycle together with the energy cycle, together with the carbon cycle, things become much complicated. If we look at a subset, it is easier, okay? And this is why traditionally, especially in a period with limited computational resources, we used to split the processes in subsets. And as I said, this is called a reductionist view. And if we look at the web page, just let me put it in your screen. If you look at the web page, there is a link on reductionism, a Wikipedia page, which gives this example of a duck that is described mechanistically through an aggregation of parts. Okay, and this is something that is not realistic, obviously, because the body of a living organism cannot be split in parts. Of course, we can do that, but they are so interconnected that in a modern vision, we have to look at the aggregation of everything in a living organism, because if we only look to the liver, for instance, or only look to the heart, we may miss important links. We may not understand why the heart at a certain point is failing. Okay, so this aggregated view is called the holistic view. And there is another link, a Wikipedia page. You see here, holistic. No, it's not a Wikipedia in this case. It's a link to dictionary, to Cambridge Dictionary. So holistic means dealing with the whole of something and not just a part. Okay, let's focus on these terms, because holistic approach today is a buzzword. When you talk about environment, about climate, you will hear very frequently people saying, I am taking an holistic approach to it. It's a buzzword. It is very fashionable today, this kind of approach, which was not used in the past. And the holistic approach allows to understand the links between parts of a system, allows to understand the whole functioning. On the other hand, there is a problem with the holistic approach, which I already mentioned. It is very complicated. It is very problematic because, first of all, these links, sometimes we don't understand them. And we have a limited knowledge of these links. And therefore, if we make the attempt of describing everything, we may lose the details of the single parts. So be careful, because this kind of approach, this buzzword, may bring you to lose the perception of your specific need, of your specific goal. So if your perception, if your goal is to improve the health of your heart, of course, you need to study all the connections between the art and our body. But on the other hand, you have to focus specifically on the art. You have to focus specifically on the cures, on the medical treatment that act over the heart. So this is to say that very often the word reductionist is used with a negative meaning, while the word holistic is used with a positive meaning. Be careful, because I think we need both. And we need both, especially because we are engineers. We have to find solutions. I say we are engineers. I hope that the students who are not attending engineering can get what I mean. I mean, if you are a social scientist, it applies to you anyway. What I mean is that very often today, when we talk about environment sustainability, we run the risk of losing the focus on solutions. Okay, so we make an effort to understand everything, to understand complexity, and we make an effort to introduce innovations in our approach, which is perfectly fine, because without innovation, we cannot move forward. On the other hand, very often we miss the focus on the solution. And this results simply in no action, which is what is occurring. If you look at the history of climate change, you see a lot of discussion at the global level. A lot of discussion at the global level, which means that there is a lot of complexity, because these discussions become very, very complex, because there are several countries involved, several competing interests, legitimate interests, but competing. And therefore, very often the result is a lot of discussion and no action. While at this time, today, we need to act also at the local level. So we bring the discussion at the global level, and we forget the solution at the local level, and then people get flooded, and then we get droughts, and then everything, you know. So let's keep in mind that we have two different approaches: a reductionist approach, an holistic approach. They have both pros and cons. We need to make an integration, an optimal integration. Now, let me go back to the PowerPoint and sorry, presentation here. Okay, you see there are many components in the Earth system, and they are interrelated. So let's have an holistic view. We have the sun, which is providing the energy that fuels all of these processes. Without the sun, everything would be died, okay? And without the energy that is given by the sun. Keep in mind the Earth system takes the energy from the sun. Some energy also comes from internal heat, but it is very limited. The energy, the most prominent source of energy is the sun through solar radiation. And then there are all of these processes, which we are not describing here in detail, because we will focus on some of them in detail later. But of course, you see the water cycle, and also there is the water cycle includes heat exchange, evaporation, precipitation, and also there is the carbon cycle. The carbon cycle has a relevant role in driving the climate. It is the cycle of the CO2, which is stored in fossil fuels, in fossils. It is stored into vegetation. It is stored within the earth, and part of it is released into the atmosphere. Part is absorbed by the oceans. So there is a cycle also for the CO2. Okay, the CO2 is a natural component of our system, and like water is a natural component of our system. And then there is the interaction between the water cycle and the carbon cycle, which is extremely important because, as I said, the carbon is stored into the oceans, and there is an interaction with the energy fluxes. Okay, let's now forget the holistic view for a moment, and let's take in order to better understand these single components, a reductionist approach. This slide, I can skip it because I already discussed about the reductionist approach and the holistic view. Now, if we adopt the reductionist approach, usually the Earth system is studied by subdividing it in the so-called spheres. The spheres are subset of processes. And the spheres that are traditionally considered are the atmosphere. Okay, so you understand why spheres. Okay, the atmosphere, the atmosphere includes, is governed by atmospheric processes. And then there is a geosphere. Here there is a spelling error, I'm sorry, there is a missing H. I will correct it. And then the geosphere refers to the processes that occur over and within the Earth. So, I mean, volcanoes, the flux of magma is described through the geosphere, and also geology, lithology is part of the geosphere. And then there is the biosphere, which describes the processes that are related to living organisms. The hydrosphere is the sphere collecting water processes. And you see that there is an interaction between these spheres. There is some overlap. I want to make a little break and moving back to the website, because there is an interesting video that I suggest you to look at. And for a moment, I want to run it. First, the main link is that of geoscience videos. Let me click on it. These videos are interesting, are an interesting view, and I suggest you to have a look at them. Okay, so there are several videos. Let's click on the Earth system, and in the Earth system, I think there is a video on the Earth system itself. Okay, there is only one. Let me just start it a little bit, and let me just remove the audio, and it talks about 4 spheres, and you see that they overlap a little bit. They over a little bit, and then the video, it's a short video. I think it is about 5 minutes, 7 minutes, I don't remember. And then it talks about the connections and explains how they interact. These connections means fluxes of matter between one sphere and the other. Okay, so you see matter, reservoirs, and flux. So this is an example of the water cycle. There is a flux in input flux, which is given by rainfall to the ocean, and then a flux out. And the reservoir is the ocean. Okay, and it explains how these fluxes make sure that there is connection between the spheres. As I said, it lasts 7 minutes, and also it talks about climate change. You see, it lasts 7 minutes. We are not looking at it, but have a look. I suggest that when you are studying, it's an interesting way of making a break. Good. Let me go back to the PowerPoint presentation. Where is it? Here it is. Perfect. Okay, now there are other spheres that are often considered beyond those that are also discussed in the video that I just started, which are the cryosphere, snow and ice processes, the lithosphere, land processes. One may say that the lithosphere is part of the geosphere. That's fine. Pedosphere, which is related to soil, and look at the last one. This is interesting. A recently introduced sphere is the technosphere, which includes the human processes, which today are considered to be extremely influential on the other spheres. This is the distinguishing feature of our modern approach. We believe some people have introduced the term Anthropocene to define the recent time when humans are believed to make a significant impact. Humans are believed to be a significant driving force of the other spheres of the Earth processes. This term Anthropocene has been used as a proposal to define the current geologic era. And there is some discussion about this because geologists are convinced that geologic eras should be identified basing on agreed marker in geologic records. So they distinguish the various geologic eras by looking at geologic forms, geologic markers. And therefore there is some criticism because it's not clear what would be the geologic marker of the Anthropocene. But I think the discussion is interesting, and I think it is useful to this proposal to draw our attention on the fact that humans today are indeed making a substantial impact over the Earth processes. And therefore, the introduction of the technosphere and the introduction of this term Anthropocene. Just be aware of it. It's as I said, it's still discussed. There are some people that don't believe that we can define the Anthropocene as a new era. On the other hand, as I said, I think the concept is useful. Now, it is interesting to move forward to understand how the Earth system works, to look at the connection among spheres. It is extremely interesting to look at these links. I already mentioned that links means fluxes of matter, of something. Can be fluxes of a mass, like water, can be fluxes of an entity, a physical entity like energy. So these fluxes connect the spheres. And we need to understand some more because so far it's not clear what I mean. And I think that it is convenient to adopt a reductionist approach to better understand what I mean. First of all, one possibility is, in order to understand this connection, these links, these fluxes, one possibility is to look at the carbon cycle as the agent linking the spheres. The carbon cycle, what is the carbon cycle? The carbon cycle describes the processes in which carbon is exchanged from the atmosphere to the Earth. In my website, there is a link to a video from NOAA. I'm making the break now. If you want to use 5 minutes of your break, you can look at the video. And which explains with some example what is the carbon cycle. But I think it is sufficiently clear to say that it describes the travel of CO2 from the Earth to the atmosphere, to the oceans, and again to the Earth. And so forth. The carbon cycle is a closed system. It means that we cannot get carbon from space or whatever. It is closed. There is no exchange of carbon with the outside of the Earth system. You know that there have been some proposals like to store the CO2 and launch it in the space. This is not yet doable because the idea was let's decrease the concentration of CO2 in the atmosphere. We can send it to space, but this is not really practical so far. So far the carbon cycle is closed, okay? we have energy entering the system, but the carbon, energy entering the system and leaving the system, but the carbon cannot leave the system, cannot enter the system. So the carbon cycle means that the carbon is traveling, you know, it's traveling from the Earth to the atmosphere through fluxes of carbon. And what is the fuel that is used in order to move this carbon? It's energy from the sun. As I said, all of these cycles, all of these cycling processes take their fuel from the sun. Okay. Understanding perturbation of the cycle, which is a natural cycle. I mean, even without humans, the carbon cycle was working in the past, and the demonstration is that the CO2 concentration in the atmosphere was continuously changing in the past, was continuously changing in sometime several billion years ago. Was the concentration of CO2 in the atmosphere was higher than today, because the temperature of Earth was higher than today. So it is a natural cycle, but it is perturbed by humans. And therefore, it is extremely important that we understand the carbon cycle and its perturbation. Let me see, I think here I have a picture, a simplified picture of the carbon cycle. I think that I can leave this picture on the screen and we can take a 10 minutes break up to 10:15. And then we continue up to more or less 11. Do you have any question before I turn the camera and the micro off? Okay, if you elaborate any question during the break, would be great. Okay, otherwise I elaborate a question for you. So let's take the break. Thanks. Okay, good. Thank you for replying to the poll, which I put in the chat. I will try to make use of the polls to stimulate your reaction. And yeah, your replies match what I was expecting. So sometimes, yes, I see some of you indeed who noticed that, and sometimes I am too trivial. Yeah, I know that. I anticipate that on Monday I will be less trivial, but I also want to make sure that I don't leave anyone behind. Okay, good. The poll is in the chat. You can take your time to reply, and most of you already replied. Okay, so carbon cycle, and you see in this figure some of the fluxes due to natural exchanges. Natural means not caused by humans, but you see that there is also a huge, in this figure, a huge component that is of exchanges that is human induced. In fact, we all know that by, for instance, burning the fossil fuels, what we do is to extract CO2 that is stored in the underground and release it to the atmosphere. This happens also naturally because sometimes we have fires, even when we burn woods or trees. Of course, we release CO2 in the atmosphere, and also there might be some spontaneous fires that fuel this exchange of CO2. But as you know, we believe that the extraction of fossil fuels, which has been massive in the past 100 years, contributes to increasing the concentration of CO2 in the atmosphere. There have been several solutions that have been proposed in order to reduce the CO2 concentration in the atmospheres, and one of these is to restore, to re-inject the CO2 in the underground after capturing it from the atmosphere. So there has been a lot of studies on carbon capture, because of course by capturing carbon we reduce the concentration of carbon in the atmosphere, but then the problem is where to store it, and there have been ideas to use facilities that in the past have been used to extract the fossil fuels, to use the same facilities to re-inject the CO2 in the underground. However, this solution is still debated because there is no assurance that the CO2 remains in the underground once it has been injected, because you know, there are cracks in the underground, there are cracks in the rock layers, and also there are pores in the soils, and therefore it might be that the CO2 travels back to the atmosphere spontaneously. So it is, these are examples of human-induced fluxes. I think here it's not emphasized enough the contribution of the ocean. The oceans are contributing a lot to storage of CO2 and release of CO2. And the capacity of oceans strictly depends on the temperature of the ocean. So to give you an example of a feedback, that is, feedback means a response to a perturbation. So to give you an example of feedbacks, let's assume that temperature is increasing because humans have increased the CO2 concentration in the atmosphere. The temperature increase implies an increase of temperature in the oceans, and then a release of CO2 from the oceans, which further contributes to increasing the CO2 concentration in the atmosphere, and therefore further contributes to global warming, which once again hits the ocean, so fueling a vicious cycle, a cycle that tends to reinforce itself. This kind of mutual reinforcing is what we call feedback. So the feedback is in this case, the negative feedback is the additional release of CO2 from the ocean after global warming, which reinforces global warming. This is the feedback. And these feedbacks, when they are negative, are, particularly concerning, because it means that after a small perturbation by humans, we can experience a very large impact of this small perturbation, which reinforces itself. Another example is resonance. Resonance for instance, of a bridge. We know that the soldiers, when they walk over the bridge, they break their rhythm, their pace, their walking pace, because they cannot walk everyone at the same time with the same leg. Why? Because they are giving a synchronized perturbation to the bridge, which may reply by amplifying its oscillation, because the frequency of the walk matches the frequency of oscillation of the bridge. And therefore, we may have a bridge collapse if the soldiers walk with the same pace. The same thing for the human perturbation to the carbon cycle. A small perturbation may originate a large impact because there is a feedback that reinforces the impact itself. This is important to be understood, but anyway, I think going back to my initial reflection, the contribution of the ocean is not emphasized enough in this figure, which emphasizes the human contribution, which is fine. Now, another possibility to look at the links between the spheres is the water cycle. This is something that we know a little bit better, because the water cycle is traditionally taught all over the world in the primary school. And I don't think there is the need to comment on what we see in this figure. And the only thing that I note here is that there is the energy from the sun, which fuels also the cycle, which goes through precipitation, and then precipitation which can be in the form of rain or snow, and river flow, water flow in general over the land after precipitation, and then storage in the oceans, evaporation from the land, and the transpiration from the trees, from the vegetables. And then there is again, after evaporation, the condensation, and then precipitation again. This is another way at looking at the connections between the atmosphere, the geosphere, the pedosphere, the cryosphere, etc. And it is also in this case interesting to look at the links, at these exchanges of matter. In this case, the matter is water. In the previous case, the matter was carbon, and exchanges of energy. We need a continuous exchange of energy to fuel this cycle. Another example is precisely energy exchanges, and they allow us to see energetic connection between the spheres. So we have energy from the sun through radiation, and then the ground gets heated, and the energy is transferred in the form of heat from the ground to the air through conduction. Conduction is exchange through contact, and convection. Convection is a flux originated by movement. And for instance, the movement of warm air brings the energy in the atmosphere. And also energy exchanges are something that is interesting to give the idea of these connections, of the complexity of this connection. What I really want to emphasize is that we need to understand and then describe these connections, possibly within an holistic view. And therefore, you understand the complexity of what we have to do. And keep in mind that also in terms of understanding, it looks trivial. Let me go back to the previous slide. It looks trivial here, because as I said, we know the water cycle from the primary school. On the other hand, as I mentioned at the beginning of this lecture, there are still many details that we don't know about the water cycle, which is very simple, but still we don't know how this fluxes, how these fluxes articulate, how long do they take. I want to give you another interesting example. We talked about groundwater some minutes ago, and we don't have any means to estimate the volume of water in the underground. Groundwater is one essential water source for civil use and agricultural use. It is essential for producing food, but in terms of sustainability, we don't know if our current use of groundwater is sustainable, because we cannot make a mass balance. We cannot make a balance because we don't know the volume of water that is stored in the underground. This is something that is impressive. It is an essential information. How can we judge whether our water use is sustainable if we don't know how much water do we have? But this is the reality. We really don't know how much water is stored in the groundwater at a given location. We may have an idea of the global amount, but at a given location, we don't have an idea. Okay, these numbers of energy exchanges are interesting to give you an order of magnitude. You don't need to learn them by memory, but it is interesting. If we assume that the energy from the sun is equal to 100, you see that 20% of it is reflected by clouds back into the space. And then the 29% is absorbed by the atmosphere, 4% is absorbed by clouds, 47% is given to the ground. Okay, and then we have 7% which is reflected by the surface, 47% is absorbed, and then you look at the other exchanges. So basically we have an emission of energy by the surface which is equal to 116, of which something is emitted directly back to space, and some dominant quantity is absorbed by the atmosphere. And then, of course, this is balanced. And then you have an idea of what are the most important energy exchanges. Okay, of course, there is some of these fluxes are reflected back. So what is absorbed by the atmosphere then is emitted back to the Earth, etc. Everything is balanced, but you see that the complexity is indeed there. Now, let's now get into something that is less trivial, okay? And given that also we need to discuss something about engineering in a understandable manner. Let's get into something that is not really trivial, and in order to try to be more technical. So let me just jump back one slide. We had examples of these cycles, okay? And what I said is we need to understand conceptually these cycles. We need to understand these fluxes. Why we need to understand them? Because we need to describe them. We need to get a mathematical representation. Why? Because if we want to adapt to climate change, we need to make design. We need to know the numbers of these processes. We need to know the number of the human impact. We need to know the numbers related to water, how less rainfall we will get into the future. We need to get a number. So if I want to estimate the impact of a flood, I need to get a number, how much water, the volume of water that I got from the flood. So to get this number, we have to explore Earth system dynamics. Earth system dynamics, the dynamics is the physics of these processes. It means the description of these processes. The dynamics is mathematics, okay? And the problem is extremely tough. It is, there are so many links, so much complexity, and here there is another spelling error, strong non-linearities and tipping point. Now, I want to conclude this lecture by maybe that we have some time left, so it's not a conclusion really, but I want to dedicate a part of this lecture to understand what is non-linearity and what is a tipping point. If you are interested in climate change, you heard many times about non-linearity, non-linear processes. You heard many times about chaos and tipping points, because these are concerns. These are concerns related to climate and climate change. So we need to understand what we are talking about. What means non-linearity, what means chaos, what means tipping points. Okay, so non-linearity. What is non-linearity? Now let me take, give me 1 minute, a graphic blackboard, because I think the concept requires some more interaction. So 1 second, because I need to go to OneNote, and here it is. And I need, after going to OneNote, I need to share the screen of the graphic blackboard. So let me share it. Okay, here it is. Perfect. Just 1 second, because I need again to go to OneNote. Okay, now you should see my graphic blackboard. If this is not the case, just let me know. And there is written climate change adaptation in the upper left. And let me take a pen here. Okay, so what is non-linearity? So just 1 second. Non-linearity. Non-linearity. Okay, what is non-linearity? Non-linearity, let me make a graph. Let's suppose that we want to make a graph of let's make a graph of like, for instance, CO2 concentration. And here on the vertical axis, we may put like an indicator or something like this, like global temperature. Okay, global T. Basically, let me think about it. Let me make an example that is something easier to make. Let me start not with CO2 concentration, but let me start with time, okay? Because this is a graph that we know. Okay, global temperature and time. Okay, so let's suppose that we start from 1850, and here we are about 2022. And we saw that this graph, it is something like this, okay? Perfect. Now, this is an example of a process that is non-linear, because linearity, it is expressed over a graph as a straight line. So this is a linear increase, or this is a linear pattern. And when I have something that cannot be represented through a straight line, it is nonlinear. Now, let me make the previous example. Let me draw a straight line for a graph, okay? Previous example was CO2 concentration, and here there was T, okay? Let's suppose that the relationship between CO2 concentration and temperature is linear. It's a straight line. This is concerning because we see that with an increase of CO2, we have an increase of global temperature. On the other hand, it is something that can be easily predicted. So we can say, fine, if I make a prediction of the CO2 concentration into the future, I can also predict the temperature. And linearity has this nice feature. It is something that is changing in a regular way so that it can be easily predicted. Good. Now, let's instead suppose that we have something like this. Starts linearly, and then at a certain point, there is a point where even a small change in CO2 concentration causes a striking change in temperature. This is nonlinearity. Nonlinearity means that even at a certain point, even a small perturbation can cause a big impact. This is nonlinearity. And this can be called a tipping point. What is a tipping point? It's a point after which, sorry, it's a point after which we may have a turnover, we may have a radical shift. So you understand that the presence of tipping points, the presence of linearity is a matter of concern. It's a matter of concern because you cannot easily predict the future in a similar situation. And it's a matter of concern because we know that there are tipping points in the Earth system. For instance, let me make an example. The desert areas, in the past, they were not desert. In the past, there was some precipitation. Some of them in the past were covered by a lot of vegetation. There was precipitation. Precipitation stimulated vegetation. Vegetation stimulated evaporation. And evaporation reinforced precipitation. But once that you decrease precipitation, you get less water for vegetation, less evaporation. And until the vegetation survives, the perturbation is limited because vegetation continues to evaporate, less evaporation, but still there is evaporation. So there is still a reinforcing of the water cycle. Vegetation is suffering, but still the vegetation may decrease its density, but still the equilibrium is preserved. After a certain point, if you continue decreasing rainfall, vegetation dies. And the dying vegetation means that you don't have evaporation anymore and everything is blocked and the area becomes desertic and you cannot go back. So this is a tipping point, okay? And now you understand the key role of tipping points and nonlinearity. Let me give you, okay, let's wait for give you another interesting example of a tipping point. Before giving you the other interesting example, let's define nonlinearity in a mathematical way because we need to understand how to describe linearity and nonlinearity mathematically, okay? So when we display these graphs, we are displaying what are called in mathematics functions. Okay, and these functions can be expressed in this way: y is equal to fx, and where x is the independent variable and y is the dependent variable. So in this case of the graph here, I may write that T is f of CO2. Okay, and so in general, let me stick on this representation. Y is fx. Okay. Linearity means that we can write means two things. So let me define the linearity. Linearity means two things. First, two conditions. One, f x plus y is equal to fx plus fy. Okay, this is called the superposition principle. In Italian is principio di sovrapposizione degli effetti. It means the superimposition principle. It means that, talking again about CO2 and temperature, if you have an increase of CO2 caused by humans and an increase of CO2 caused by natural causes, the increase in temperature is given by the sum of the two contributions. So if I get 1 degree of temperature increase given by humans and 1 degree of temperature increase given by natural causes, the overall increase is 2 degrees. This is the sum of the effects, okay? And it is what is called here in the first condition in blue. It is this one, okay? Which may be not true, because you may have a 1 degree caused by humans, a 1 degree caused by natural effects, but if you sum them in correspondence of the tipping point, you get an increase that is much higher than 2 degrees. Okay, so with a process that is non-linear, the superimposition principle is not it's not true. Okay. Now there is a second condition for linearity. F a x is equal to a f x. So these are two necessary and sufficient conditions to define linearity. Good. Okay, we have to understand this because in mathematical terms, we need mathematics to build our models, to build our prediction models. Okay, so be careful about nonlinearity. Okay, now that we understood a little bit more, also in mathematical terms, what is linearity, what are tipping points, let me relax you a little bit by giving you another example of a tipping point that was recently passed. Okay, so let me now share once again the screen of, 1 second, of the web page. Okay, here it is. You should see now again the PowerPoint presentation with Earth System Dynamics. And let me open here another web page and let's look on Wikipedia for Wikipedia Aral Lake disaster. This is a relevant example, very well known, and let's this is in English. Let's yeah, in English. So this is the Wikipedia page describing the disaster of the Aral Sea. Okay, so look at the picture. The Aral Sea in 1989 and 2014, it's almost disappeared. Okay, it was formerly the 4th largest lake in the world, with an area of 68,000 square kilometers. Just to give you an idea, it's about the north of Italy. The north of Italy is about north of the Po River. It's about probably a little bit less than 68,000 square kilometers. It began shrinking in 1960 after the rivers that fed it were diverted by Soviet irrigation projects. The reason was that they tried to promote the cultivation of cotton because it was very convenient at that time, but cotton needs a lot of water, and therefore they diverted the rivers and used the water from the rivers for irrigation, which is, I mean, it is something that is done in large part of the world. But here they couldn't predict the non-linear effect, the tipping point that actually occurred. You see that by 2007, it had declined 10% of its original size, splitting into 4 lakes. And the problem is that they tried to solve the disaster to replenish the lake with additional water, but the problem is that now they are missing the contribution from evaporation, so the climate is changed in the area. So the problem cannot be solved by simply reactivating the flow in the rivers, because there is less flow in the rivers now because there is less rainfall. The local climate is changed, and therefore it looks like the situation is irreversible because they passed the tipping point, and it was not really predictable. So look at some pictures here. I think there are some pictures. Okay, these are pictures of the area of the lake, and you see there are abandoned ships, and there is a dominance of salted areas. They cannot be, you see the white area is salt, it cannot be cultivated. You see the white from space, it's salt, because it was actually a salted lake, because it's so large that it got some salinity. And here is an example of a cotton cultivation, you see. And here, okay, several pictures of the shrinking of the lake. A similar problem. Wikipedia, Urmia Lake. A similar problem that is ongoing now. Lake Urmia. The problem is similar. You see, it is shrinking. And now they are trying to revert the process because probably here we are still in time. You can have a look in order to get an idea of another tipping point. Okay, now let's go back to the presentation here.
Sorry, can I ask a question?
Yes, please. You should.
Does the tipping point always implies an irreversible situation, or is a sort of situation that happen very frequently but not always imply this irreversible situation?
Okay, the answer is the second. It doesn't always imply an irreversible situation. You know, the problem of the tipping point is that the system passes from an equilibrium state to another equilibrium state. So the Lake Aral now, it's in equilibrium. It's in equilibrium because there is less precipitation. Precipitation went somewhere else, maybe also for the effect of climate change. And there is less precipitation and less river flow and less storage. It's another equilibrium state. So basically, this is described. Okay, I don't think it is worth that I make a sketch, but anyway, it can be easily shown with a sketch that a system may have several equilibrium states, and the transition between one equilibrium to another equilibrium can be reversible or not. But sometimes it's not easy to predict this. So for instance, and it's not easy to create the conditions for for inverting the transition. Like, for instance, if we were able to bring a lot of water in Russia into the Lake Aral to create a storage that reactivate some mechanisms of exchanges of water from the lake, the atmosphere, and precipitation, then if the process is restarted, we can go back to the previous equilibrium in this case. But it is practically impossible to bring all this volume of water there. It's impossible. So, I mean, in principle, they can be reverted. This is not always possible.
Okay, thank you.
Okay, perfect. If there are any other questions, please step in. And here you see in this figure, which is reported in my web pages, some tipping elements that have been identified in the Earth's climate system. I see a raised hand. Magdalena, do you have a question?
Yeah, sorry. I just wanted to ask if there has been any instance where reaching a tipping point and changing the equilibrium was actually beneficial for humans, or is it always a bad thing that we should be kind of worried about?
Okay, I got the echo for a while. No, I think you made a very interesting question, because we try to associate climate change and therefore the change of the state of a system to a negative effect. Actually, there are several examples where climate change has brought a beneficial effect. For instance, it can be demonstrated if you look, and there are researches on that, there are also publications. If you make an assessment of the level of development of ancient civilizations, like the Roman Empire, and you study the correlation between the development of the Roman Empire and the collapse of the Roman Empire and the global temperature, there are interesting studies that demonstrated that the Roman Empire developed and reached its max extension during climate optimum. And there are assumptions, hypotheses that the collapse of the Roman Empire was caused by a deterioration of climate. We know that during the Roman times, we had a climate optimum. For instance, this is proved by the fact that in the Alps, the altitude of woods was higher than now. For instance, the Matterhorn, the Monte Cervino in Italian, which is called in English Matterhorn, the name, the Italian names, means a mountain covered by woods, which is not the case now. And so there are some remains that prove that there was a climate optimum, and it was co-occurring with the max development of the Roman Empire. There are also remains that prove that after the year 500 after Christ, there was a deterioration of climate up to the year, which lasted about 500-600 years. And then in the medieval period, after the year 1000 up to the year 1400, there was a warming, at least in Europe, because we have this information more from Europe than from the Americas. So basically, what I want to say, there are studies that prove that ancient civilization flourished in a period of climate optimum and experienced recessions in periods in cooling periods. Today, what we can observe is that in the north of Europe, for instance, the climate is much more favorable to socioeconomic development after the global warming. The situation, of course, is not the same in the south of Europe. In the south of Europe, it becomes it becomes more challenging. So what I want to say to reply to your question, no, crossing a tipping point doesn't necessarily mean that you get to worsened state. And the situation can be reverted. In the past, we had other period where the Earth was without ice caps, and then the ice caps reformed. But there is to say that these changes require adaptation. We are studying climate change adaptation. Adaptation means that the societal context should adapt to it, should change accordingly. And if the change of climate is very rapid, the societal context cannot really adapt quickly. And meanwhile, there might be some social tension, migration, deterioration of the relationship between countries, among countries. And therefore, you know, this kind of adaptation, if the climate change is very rapid, maybe indeed may have a strong and a negative impact. I hope I replied to your question. Maybe I was also too long, but I like to discuss.
Thank you.
Yeah. Okay. Now, you see example of tipping points here. I'm not making any comment on them because I think they are quite clear. Like you see the Sahara greening, the West African monsoon shift, the dieback of Amazonas rainforest. You know that we have the feeling that if we continue to reduce the extension of the Amazonian, then we may get to a situation where the forest is not able to self-sustain itself in terms of evaporation, precipitation, needs for water, etc. And so these tipping points, some of them can be reverted, some other easily reverted, some other in principle can be reverted, but it's not easy. And therefore you understand why they are concerning, and they are strongly connected to non-linearity. Okay, before I move forward to this, sorry, here there is no mention to chaos, and let me just spend a few words. Chaos is the result of non-linearity, which means that a small impact, a small perturbation can create a very relevant impact. This is chaos. And an example of chaos was given by Lawrence, who introduced the so-called butterfly effect. I think you know it. If a butterfly flaps in Japan, then a tornado is caused in the United States, which means a small perturbation in the climate system induced by the butterfly who flaps then turns out in a strong impact, which is amplified by non-linearity, amplified by the chaotic behavior of the system. For our purpose, you can consider chaos and non-linearity as synonyms. Actually, chaos is the result of non-linearity. They are not really synonyms, but for our purpose, let's take them as synonyms. I just want that you know, you are aware of the meaning of this term, which is frequently used when talking about climate. Okay, one way also to look at the connection between spheres is to look at the social system or social cycle, okay? And it is interesting because it highlights what is the connection between the social system and the other spheres. So the connection between the technosphere, if you want to call it in this way, and the other spheres. And these connections are ensured by human activities. And there is not much to say here. The figure is self-explaining. We will focus in more details with this connection on these connections later on. So I'm not spending much time now. I just wanted to give you this example, which is not usually given, So another way to look at the connections between spheres. Okay, now, as I said, we need to describe mathematically these links, these processes, and also the social system. And this is an effort that is highly interdisciplinary, and this is why I am excited also by the presence of a multidisciplinary audience in this course, because it has been widely recognized that a connection between earth sciences and social sciences in the widest sense, including economics, etc., is necessary in order to get a satisfactory representation in mathematical terms of the connection of the different spheres, which means to get a satisfactory holistic representation of the Earth system. I'll stop here for now, and then I will continue on Monday with these final slides. There are not many in this PowerPoint, but it's already 11, so I prefer to stop here. Do you have any questions for me?
May I have a question?
Yeah, please.
Do I have to come to classes in presence on Monday?
No, it's not needed. It is not required. So basically, frequency attendance to the classes is not required. Either physical attendance or online attendance. On Monday, I am streaming anyway. You can free to come in physical presence, to attend online, or not to attend at all because you have the videos later.
Ah, okay. So even if I don't come to classes, but I can get the exam only.
Yes, yes. The answer is yes.
Okay, and I can find the sources on Virtuale maybe.
Yes, the sources on Virtuale better on my website, which is a mirror of Virtuale. And so if you go to www.albertomontanari.it, you find everything.
Okay, thank you so much.
Also the videos, no problem. Other questions? Okay, grazie, thank you. See you on Monday, room TA10 in Via Tercini. I will upload the video soon, the video of today's lecture. Thanks, ciao, bye-bye.
Thank you.
Bye,
Bye.
thank you.
Bye.
Ciao.
Bye.